A really warm welcome to you, our listener. Thank you so much for joining us for this deep dive.
Yes, we are so glad you are here with us today.
We're basically jumping straight into a staggering reality today. I mean, think about this. 75% of the crops grown around the globe depend on animal pollination.
Which is just a massive, massive portion of our food supply.
Right. And we also know that modern agriculture heavily relies on pesticides, which, well, they are devastating those exact same pollinator populations.
Yeah, it really does feel like an unsolvable deadlock sometimes, you know?
It totally does. But today, our mission, as always, is to take a stack of dense sources and extract the absolute most important nuggets of knowledge to give you a shortcut to being well-informed without the dreaded information overload.
Exactly. And the source we have today it's really something else.
It is. We are looking at a brand new 2026 study from the journal Environmental Chemistry and Ecotoxicology, and it's titled Timing Matters. Nighttime pesticide application reduces honeybee exposure and acute mortality.
Such a great paper.
And the premise is wildly provocative. Like, what if a massive part of the solution requires zero new chemicals and, zero new technology?
Right, which is usually where everyone looks first.
Exactly. What if the answer to saving our honeybees is simply setting an alarm clock for a different time of day?
It is a beautifully elegant hypothesis, I have to say,
Yeah.
because, we are so used to looking for high-tech, multi-billion-dollar synthetic solutions to ecological crises.
Oh, absolutely.
So the idea that we might just need to shift our agricultural scheduling to the night shift is, well, it's very compelling.
Yeah.
But of course, proving a behavioral and chemical shift like that requires an incredibly rigorous setup.
Right, because you can't just, go spray a random open field at midnight and casually observe what happens the next morning.
No, not at all. The variables would be absolutely impossible to control. You've got weather, wind, random insect migrations.
Which brings us to the methodology. And I really love how they design this. It is essentially a highly controlled Truman Show for honeybees.
That is a great way to put it.
The researchers conducted this semi-field study in France across 2023 and 2024, and they placed standard honeybee colonies, Apis mellifera, inside these massive 100-meter-long insects-proof mesh tunnels.
And, the sheer scale of those tunnels is what makes the data so viable. Inside, the researchers cultivated 48 square meters of blooming Phacelia flowers.
And Phacelia is like catnip for bees, right?
Basically, yeah. It's highly attractive to them. It produces abundant nectar and pollen. So what you have is a completely enclosed private world that still authentically simulates real-world foraging conditions.
Which is key.
Right. And once the colonies acclimated to their new territory, the researchers introduced the chemical variable, which was a common foliar insecticide called karate K.
Okay, let's unpack this, because foliar, meaning it is applied directly to the foliage, the leaves and the bloom.
Right, exactly where the bees are going to land.
Exactly. And karate K is not some gentle, experimental, eco-friendly formula. It's a heavy-hitting commercial product.
It really is. It contains two active ingredients. You have pyrimecarb, which is relatively less toxic to bees, but then you also have lambda-cyhalothrin.
Right, the pyrethroid.
Yeah, and that one is a highly toxic pyrethroid. And they applied this at a standard farming rate of 1 liter per hectare.
So they aren't treating the bees with kid gloves here. They're
No.
going all in.
No, they really aren't. And that field-realistic application rate is the entire anchor of the study. A lot of lab research uses isolated artificial dosing, which farmers often, well, they just dismiss it as unrealistic.
Sure, they say, well, that's not how we do it in the field.
Exactly. But here, they are mimicking standard agricultural practice. So they took these enclosed colonies and split them into 2 treatment groups.
Okay, lay out the groups for us.
So one group's field was sprayed at 1:30 p.m., right at peak daytime foraging, and the temperature inside that tunnel was sweltering, hitting between 32 and 34 degrees Celsius.
Oh, wow, that is hot. So we have a daytime group getting blasted at peak heat while they're out working. And logically, the other group is testing the nighttime hypothesis. So their Phacelia flowers were sprayed at 9:30 p.m.
Yep. The sun had set, the bees were theoretically done for the day, and the temperature had dropped to a much cooler 18 to 20 degrees Celsius.
And those temperature differences, they end up playing a massive role in the chemical interaction later on. But to even measure the impact of the timing, the researchers needed flawless demographic data on the colonies.
They did. You can't just guess how many bees survived.
So let's talk about that tracking system, because this is where the engineering gets just Incredible. I mean, if you want to claim that spraying at night saves bees, you have to know exactly how many individual bees are leaving the hive and how many are making it back alive.
Right, down to the individual bee.
Right. So they use these video-based bee counters manufactured by BeeGuard and Apanoff. And looking at the schematics in the paper, I can only really describe them as high-tech airport security turnstiles for insects.
That is, that is a perfect visualization. The devices are these modular blocks installed directly across the hive entrance.
So they can't just bypass it.
No, the bees cannot simply fly in and out in a giant swarm anymore. They are forced to walk through these very specific, narrow corridors that are exactly 7 millimeters high.
Wow, just 7 millimeters. So it's basically forcing them into a single file line.
Exactly that. The physical height restricts them from crawling over one another's backs, which, believe it or not, is a huge common problem in insect monitoring.
I can imagine. It's just a chaotic pileup otherwise.
Exactly. So as they pass through this bottleneck, an embedded, low-power artificial intelligence system analyzes the video feed in real time. And the tracking algorithm doesn't just register, like, general movement. It actually reconstructs the vector trajectory of every single bee.
Meaning the AI knows the difference between a bee walking outward to forage, a bee returning home, and a bee just like pacing back and forth near the entrance trying to make up its mind.
Yes, it tracks the exact intent of the movement.
The precision metrics on this are just wild to me. The system operates with 99.89% precision. It makes roughly one single counting error for every 1,000 movements.
It's phenomenal tech.
And it updates the colony's pulse every minute. That is a level of granular surveillance you just rarely see in ecotoxicology.
And honestly, that real-time pulse immediately addressed the foundational assumption of the entire study.
Right, the nighttime question.
Yeah, because the concept of spraying at night only works if the bees are actually inside the hive. If a significant portion of the colony is, engaging in nocturnal foraging out in the dark, a 9:30 p.m. spray could still be disastrous.
Right, you'd just be poisoning the night crew. But the baseline AI data shut that concern down quickly.
It did.
It showed that nocturnal flights accounted for less than 1% of the total daily exits. So the bees are, they're effectively tucked in and dormant once the sun goes down. The coast is entirely clear for the tractors to roll in and spray.
Yep, the baseline is clear.
But, and here's where we get to the real meat of the study. The behavioral data from the daytime spray group, the bees hit at 1:30 p.m., is where the results take a really counterintuitive turn.
Oh, the flight activity numbers are striking. Because you would reasonably assume that a colony sprayed with a highly toxic nerve agent would experience an immediate collapse in activity.
Right. If I get hit with a severe toxin, I am going to be incapacitated. I'm not going to work.
Exactly. But the AI turnstiles showed the exact opposite.
Yeah.
Over the 24 hours following the daytime spray, the colony's flight activity didn't drop at all. It spiked.
It went up?
Yes, it increased by 26.7% compared to their baseline.
Wow.
Meanwhile, the group sprayed at night showed a 12% decrease in flight activity the following morning. And by day 3, both groups had returned to their baselines. What's fascinating here is how we interpret those contrasting numbers.
Wait, if the daytime bees are being poisoned by highly toxic chemicals, why on earth are they flying more? Shouldn't sick bees stay in bed?
It's a great question, because a 26% increase in activity sounds like the bees are, energetic and productive.
Yeah, like they had a bunch of espresso.
Right. But in reality, we are looking at the symptoms of severe neurophysiological stress.
Oh, wow. Yeah.
Lambda-cyhalothrin is a pyrethroid, meaning it targets the insect's nervous system by binding to their sodium channels. It essentially locks those channels open, leading to appetitive nerve discharges.
So that spike in flight activity isn't happy, productive foraging. It is essentially an agitated, chemically induced panic. The bees are suffering from motor tremors and hyperexcitability.
That is the direct physiological response, yes.
Yeah.
But we also have to consider the colony-level behavioral response, specifically a phenomenon known as compensatory foraging.
Compensatory foraging. How does that work?
So when foragers go out, get poisoned, and fail to return, the incoming nectar and pollen suddenly drops. And the hive operates on complex chemical and pheromonal signaling.
Right, they communicate constantly.
Exactly. So recognizing a catastrophic drop in food income, the colony basically panics. They forcibly recruit younger, surviving bees to leave the hive and make up the deficit.
Oh, that is tragic.
It is. They are desperately working overtime to save a starving hive.
That paints a grim reality, behind that 26% spike. I mean, they're sending out emergency waves of workers into a completely toxic field.
Exactly.
And looking at the nighttime group, that 12% decrease the next morning makes total sense in contrast.
Yeah.
Because they weren't hit with a fresh spray, so they aren't experiencing that acute, hyperagitated panic.
Right, no direct blast.
But they are still interacting with some residual chemicals on the flowers when they go out the next day, which leads to delayed sublethal neurotoxic effects. So their motor functions are just sluggish, navigating takes longer, and so the overall traffic just slows down for a day before they recover.
That's exactly it. The flight activity gives us a brilliant diagnostic window into the colony's health, but, as you often point out, behavior only tells half the story in toxicology.
It really does. Because the ultimate metric isn't how frantically they are flying. It is how many are actually dropping dead.
Yes.
And the mortality data is where the timing in the application shows its true stakes. Because for that 1:30 p.m. daytime spray, the AI counters recorded an astonishing 185% increase in bee mortality over the first 24 hours.
Which is devastating.
It is. The death rate more than doubled, and that elevated hemorrhaging of workers persisted for 3 consecutive days.
And comparing that to the 9:30 p.m. nighttime application provides the most critical data point of the entire paper, in my opinion.
Yeah, let's hear it.
For the nighttime spree group, there was no detectable increase in mortality.
Not at all.
None. The death rate remained completely stable at normal baseline levels, both in the first 24 hours and over the subsequent days.
Here's where it gets really interesting, though, because it requires us to look at the actual chemical residue the researchers found on the bees.
Right. The residue analysis is key here.
So for the daytime group, the colony that is losing bees by the thousands, the lab analysis found an average of 3.44 nanograms of lambda-cyhalothrin on the foragers.
Yeah.
But based on standard laboratory toxicity metrics, 3.44 nanograms is a remarkably small amount. Like, it represents less than 10% of the established contact lethal dose, the LD50, and less than 0.5% of the oral lethal dose.
They're tiny.
So if they're absorbing less than 1/10 of what is supposed to be the lethal dose, why are they dropping dead by the thousands?
This raises an important question about how we historically regulate agricultural chemicals.
Mm-hmm.
The LD50 metric is determined in a pristine, temperature-controlled laboratory setting.
Right, it's very sterile.
Very sterile. A bee is isolated, it's dosed, and it's observed in comfortable conditions. But the semi-field study introduces compounding environmental stressors, and primarily the temperature.
Ah, the 34-degree heat of the afternoon.
Exactly. That heat fundamentally alters the biological reality of the exposure. High summer ambient temperatures severely exacerbate the toxicity of pyrethroids. Yeah, the bee is already experiencing immense metabolic stress, simply trying to fly and forage in those sweltering conditions. And furthermore, the heat can actually increase the permeability of the insect's waxy cuticle.
Oh, meaning it absorbs faster.
Yes, allowing the chemical to penetrate the nervous system much more rapidly. So a dose that a bee could easily survive in a calm 20-degree laboratory becomes an acute lethal overload when you combine it with the exhaustion and the physiological strain of a 34-degree field environment.
So the whole concept of a quote-unquote safe dose is entirely an illusion when you don't factor in the environment.
100%.
The daytime bees are taking a direct chemical hit while their internal systems are already redlining from the heat, causing basically a complete physiological short circuit.
That's a great way to describe it.
But that biological reality makes the survival of the nighttime bees even more fascinating to me.
Yeah.
Because the nighttime bees flew out at 6:50 a.m.
Right.
and they landed on the exact same Phacelia flowers that were sprayed just, 8 hours prior.
Yes, they did.
So how are they surviving the residue?
Well, the researchers answered that by mapping the timeline of chemical degradation. They sampled the environment and the bees at very specific intervals. And what they found was that between 4 hours and 20 hours post-application, the concentrations of both active ingredients, the lambda-cyhalothrin and the pyrimicarb, plummeted dramatically.
I found it really helpful when I was reading this to think about this environmental degradation like leaving a steaming cup of coffee on the counter overnight.
Oh, I like that analogy.
Yeah, because in the first few minutes, it is potent, it's hot, it's highly active. But as the hours pass, the ambient environment interacts with it. The heat dissipates into the air, the chemical structure settles down, and by morning, it has lost most of its active energy.
It's just a cold, inert liquid by morning.
Exactly. And the pesticide is going through a similar environmental sapping.
It really is. During the night, the chemical volatilizes into the night air, the morning dew disperses it, and the cooler night temperatures degrade the active compounds before the bees even wake up.
So nature acts as the first shield.
Yes. By the time the morning foragers land, the environment has already neutralized a massive percentage of the threat. But, as you alluded to, environmental dissipation is only the first half of the survival equation.
Right.
Because the bees still do absorb a small amount of that degraded residue, and that brings their own biological defenses into play.
The metabolic detoxification. This was so cool to learn about. We tend to think of bees as these fragile creatures that are completely defenseless against modern chemicals.
Yeah.
But they actually do have an internal filtration system.
They do. They possess a complex suite of enzymes, specifically the cytochrome P450 family. And these enzymes are capable of binding to and metabolizing foreign toxins.
Wow.
Yeah, it's basically a biological toolkit designed by evolution to process naturally occurring plant toxins. But it can work on synthetic pesticides if the conditions are right.
It's the old saying, right? The dose makes the poison.
Precisely. When a bee is hit by the 1:30 p.m. spray, it receives a fresh, highly concentrated acute dose that instantly overwhelms those P450 enzymes. The system just crashes.
But the nighttime bees, they are encountering a degraded fractional dose the following morning.
Exactly. Their metabolic system is not overwhelmed. The enzymes actually have the time and the physiological bandwidth to break down the neurotoxin and excrete it safely. The shift in time simply gives their natural biology a fighting chance.
So what does this all mean? When you lay out the mechanics of it, the environmental dissipation overnight, followed by the bees' own metabolic enzymes mopping up the remainder, it just highlights the profound elegance of this solution.
It really does.
We aren't demanding that farmers abandon crop protection entirely and let pests destroy their yields. And we aren't waiting decades for chemists to invent a perfectly harmless, magically selective pesticide that only kills the bad guys.
Because who knows if that will ever happen.
Right. Simply shifting the application hours leverages the natural physics of the environment to degrade the poison while bypassing that peak daytime heat that makes the chemical so deadly in the first place.
And, if we connect this to the bigger picture, the policy implications of this study are incredibly optimistic.
Yeah, for sure.
In environmental science and ecotoxicology, we are so frequently analyzing irreversible damage, it can get depressing. But this research provides rigorous, AI-validated empirical evidence for an immediately deployable mitigation strategy.
You can literally start doing it tomorrow.
Exactly. Adjusting application timing to the night is a logistical shift, not a massive technological hurdle. It effectively maintains agricultural output while drastically reducing the acute mortality of our daytime pollinators. It proves that human agriculture and bee survival can actually coexist with just a bit of better scheduling.
It is the ultimate work smarter, not harder approach to ecological conservation. I love it. But, and you knew there was a but coming. As compelling as this daytime versus nighttime data is, looking at the entire ecosystem introduces a necessary complication. Because saving the honeybees by pushing all agricultural spraying into the dark seems like a perfect fix until we consider who is working the night shift.
Ah, right. The nocturnal pollinators.
Exactly. We spend so much time focusing on the daytime honeybees, we completely ignore the moths, the beetles, and the specific species of solitary bees that are out foraging by moonlight.
Which are huge contributors to pollination.
They really are. So if we shift millions of gallons of pesticide application to 9:3 year PM, are we simply lifting the execution order from the honeybee and dropping it squarely on the nocturnal insects that are just as crucial for native plant pollination?
Yeah, that is a massive, massive unresolved question.
It really is. Solving one crisis often triggers another if we don't look at the whole board.
It's the inevitable next frontier for this line of research. Protecting the entire pollinator network is going to require an even deeper understanding of those nocturnal ecosystems before we make any massive global policy shifts.
It is a phenomenal puzzle, and it's something I want to leave you, our listener, to mull over as you go about your week. Thank you so much for joining us for this deep dive. We sincerely appreciate you taking the time to explore this complex science with us. Keep challenging the simple answers, keep looking at the bigger picture, and we will catch you on the next one.